In previous videos, we've looked at affine ciphers, a relatively simple introduction to cryptography, but a lot more basic than ones that are used in modern security systems. So here we'll look at one of the most widely used, which is RSA cryptography, named after, I think, two American mathematicians and one Israeli mathematician, the Rivest-Shamir-Adelman system. And it relies on the fact that if we've got a very large number, and by very large I might mean hundreds of digits long when written in base 10, which is the product of two primes, factorizing that, so finding which two primes were multiplied together to give this massive number, it relies on the fact that that is not a quick task, that just a simple brute force trying every possible prime and seeing if it divides it, just going through a list is prohibitively slow. But the reason it's a clever system, the reason it's widely used, is the problem of factorizing those primes is problematically slow, but if somebody has a bit of information, a sort of a foothold into that, a security key in this context, then we can rely on some of the properties that come out of Euler's theorem to actually decode messages in a way that somebody who doesn't have that security key would not be able to. So credit where credit's due. So these are two bearded and not one non-bearded gentleman. So if we start with a very large number, n, which is the product of two secret primes. So somebody knows those two primes, they calculate the product of them, they multiply them together, and they make that product publicly known, but without giving away which two numbers were multiplied to get that large number. Now you can test, of course, by dividing by 2, then by 3, then by 5, then by 7, try every prime. But in general, you'd have to get up to, well, the square root of n, which if it's hundreds of digits long, it's not going to be something that you want to be doing. Now, before I kind of go on, I just want to introduce a little bit of the strange language typical of cryptography problems. Typically, there'll be person A communicating with person B, and if somebody tries to get in the way, they're an eavesdropper. So in general, person A will be called Alice, person B will be called Bob, and anybody trying to intercept the message will be called Eve. These aren't my conventions. Cryptographers are a strange, strange breed. At this point, Alice picks two prime numbers, P and Q, but does not make these known. What she does make publicly available, though, is the product of them. She calculates n equals P times Q and publicizes the product of these primes. Now, because she, and she alone, knows this prime factorization of n, she can work out phi of n quickly, Euler's phi, because P is prime and Q is prime. Phi of n, which is phi of P times phi of Q, is P minus 1 times Q minus 1. The other thing that she makes publicly available, as well as n, the product of the primes, is a public key, E, which is an integer, a positive integer, less than phi n, and which is coprime with phi n. Now she is able to calculate the multiplicative inverse, D, which is the value D, such that D times E is equivalent to 1 mod phi n. Nobody else can do that because other people don't know phi n because they don't know the prime factorization. So if we look at the table of what is known, anybody can know n and e, but only Alice knows p, q, and this multiplicative inverse d, which is e inverse mod phi n. So now Bob is at the other end of this system, and Bob wants to send Alice a message. He wants the message to be decipherable by Alice, but only by Alice. So his message is a number which is less than or equal to n and co-prime with n. So he calls this message M. So there'd be some code which basically says this number corresponds to this letter or whatever, and he wants to pass on the message which is the number M. So if Bob calculates C, which is M to the E mod N. Remember, Alice has publicized E and she's publicized N. So he can do that. He picks his own M to communicate. He's got Alice's values for E and N. So he can calculate E to the M mod N, and he makes that message publicly available. So that is his message encrypted. So this is now the state of play, that everybody can see what N is, everybody can see what E is. Alice has told everybody that. Bob has told everybody his message encoded, which is C, which is equal to M to the E mod N. Alice knows P, Q, and the multiplicative inverse D. And Bob knows M. At this point, Alice knows Bob's encoded message C, her own multiplicative inverse D, and the two primes P and Q. So when she gets the message C, she can work out C to the D mod N and know that's the same as M to the E to the power of D mod N, which is M to the ED mod N. But critically, she also knows that ED is equivalent to 1 mod phi n. So if ED is equivalent to 1 mod phi n, then ED is some multiple S of phi n plus a remainder of 1. Doesn't know what this S is, but she knows that ED is 1 larger than a multiple of phi n. So when she starts to calculate M to the ED mod n, she can say that's M to the S lots of phi n plus 1 mod n, which is M lots of M to the phi n mod n. But Euler's theorem tells us that M to the phi n is equivalent to 1 mod n, so that to the S power is equivalent to 1 mod n. So the whole message will be equivalent to M mod n, so she can recover Bob's original message of M in this way. Now that's a fairly heavy-duty bit of theory, and in the next video I'll go through a simple numerical example of this. The whole premise, or the whole security of RSA cryptography rests on the fact that there is this asymmetry of the calculations. That somebody who knows the primes can easily multiply them to get the product. And those are two large primes I found, one of just over 4 million, one of just over 7 million. multiply them together and you'll get something just over 30 trillion. But if an eavesdropper comes in and the eavesdropper sees this product of 30 point something trillion, there is no known efficient algorithm other than just brute force trying various other primes to split that back into the two component primes. And there's different systems in terms of the size of the primes, but we're getting up towards sort of values which are over 1,000 digits long when written in base 10. And realistically, what I've written there is 7 digits long by 7 digits long, and that itself looks prohibitively problematic. So 1,000 digit ones, forget about it.